Hello everyone, welcome back to my YouTube channel Physics Unification. In the last video, we discussed some topics from the chapter Electrostatic Potential and Capacitance. Today we can continue with the same chapter Electrostatic Potential and Capacitance. First of all, derivation of expression for electric potential energy of a system of 2-point charges Q1 and Q2 in the absence of external electric field. This derivation is very important for 5 marks. Consider two charges Q1 and Q2 with position vector R12. If there is no electric field, so work done in bringing charge Q1 from infinity to R1 is 0. This charge Q1 produces potential in space becomes V1 is equals to 1 divided by 4 pi epsilon naught Q1 divided by R1p. Now work done in bringing the charge Q2 from infinity to the point P is the Q2 times the potential V1. Then W is equals to Q2 into value of V1 is 1 divided by 4 pi epsilon naught Q1 divided by R1 2. In place of P, what we have to substitute? Next charge 2, that is R12. And W is equals to 1 divided by 4 pi epsilon naught Q1 into Q2 divided by R12. Here R12 is the distance between Q1 and Q2. Now work done gets stored in the form of potential energy. Thus potential energy becomes U is equals to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R12. Let us consider this one is the expression for potential energy if we consider more than 3 charges Q1, Q2, Q3 which is located at the position vectors R1, R2, R3. Then total potential energy U can be written it as 1 divided by 4 pi epsilon naught Q1, Q2 divided by R12 plus Q2, Q3 divided by R23 plus Q1, Q3 divided by R13. If only two charges Q1 and Q2 are there, means potential energy expression becomes U is equals to 1 divided by 4 pi epsilon naught Q1, Q2 divided by R12. If three charges are there Q1, Q2 and Q3, then total potential energy becomes 1 divided by 4 pi epsilon naught Q1, Q2 divided by R12 plus Q2, Q3 divided by R23 plus Q1, Q3 divided by R13. Up to here, this derivation which carries for 5 marks. Now, potential energy in an external field. If we consider only one single charge, then work done in bringing a charge Q from infinity to the point P in the external field becomes Q into V. Therefore, potential energy of Q at R in an external field is equals to Q into V of R. Then you need V into V of R into Q. That gives the value of potential energy. Unit of energy defined it as 1 electron volt and that value which is equals to 1.6 into 10 to the power of minus 19 joule. Now potential energy of a system of two charges in an external field. Then what happens? Work done on Q1 against the external field which gives the value Q1 into V of R1. Work done on Q2 against the external field Q2 into V of R2. Work done on Q2 against the field due to the Q1 can be written it as 1 divided by 4 pi epsilon naught Q1 Q2 divided by R12. Then potential energy of the system is equals to total work done in assembling the configuration of two charges, that is Q1 into V of R1 plus Q2 into V of R2 plus 1 divided by 4 pi epsilon naught Q1 Q2 divided by R12. Third case, potential energy of an dipole in an external field. Consider a dipole with charges plus Q and minus Q placed in an uniform electric field E. In the uniform electric field, the dipole experience no net force but which experiences a torque. Then amount of work done by the external torque will be stored in the form of potential energy of the system. Then potential energy of the dipole for an inclination theta can be written it as u of theta is equals to minus p e into cos theta. That is equals to minus p vector into E, where E is the electric field and P is the dipole moment for maximum potential energy U max, which becomes plus P into E when theta is equals to 180 degree. For minimum potential energy, U minimum is equals to minus P into E. Now, potential energy of dipole. Here, U is equals to 0 when theta is equals to 90 degree. For dipole, theta equal to 90 degree. For unstable orientation, theta is equals to 180 degree, which gives maximum potential energy. For stable orientation, theta equal to 0 degree, which gives minimum potential energy. Now, difference between polar and non-polar molecules, and this difference is very important for 2 marks. Here, what do you mean by polar molecules? When the center of positive charges and negative charges do not coincide, which gives the polar molecules. We can see the examples H2O, HCl and H3N2O, and which has permanent dipole moment. If center of positive charge and negative charge coincide, those molecules are known as non-polar molecules. O2, N2, CO2, H2 are the non-polar molecules and they do not possess permanent dipole moment. Polar molecule which possesses permanent dipole moment, non-polar do not possess any permanent dipole moment. Behavior of non-polar molecules in the presence of an external electric field. If we consider in the absence of external field, the non-polar molecules do not possess any dipole moment. But in presence of external electric field, positive and negative charges of a non-polar molecules are displaced in opposite directions. The displacement stops when the external force on the constituent charges of the molecule is balanced by the restoring force. The nonpolar molecules thus develops a induced dipole moment. Therefore, the dielectric is said to be polarized by the external electric field in nonpolar molecules. But now what we have to see? Behavior of polar molecules in the presence of an external electric field. In the similar way here, in absence of external electric field, the different permanent dipoles are oriented randomly due to thermal agitations. So the total dipole moment is 0 here. But in presence of external electric field, a dielectric with polar molecules develops a net dipole moment. When an external field is applied, the individual dipole moments tend to align with the field. And overall, the net dipole moment in the direction of the external field which produces the dielectric is polarized here. Which completes the part 2 from the chapter Electrostatic Potential and Capacitance. In the next video, we can discuss the concept of capacitance and capacitor, derivation of expression for capacitance of parallel plate capacitor, definition of capacitors and capacitors in series and capacitors in. If you have any doubts regarding these concepts, please drop a comment in a comment box. Stay tuned, like, share and subscribe my YouTube channel Physics Unification. Thank you.